Hello everyone, this presentation is tips for analysis of materials, mainly metals and alloys, and it's a sister presentation to interpreting microstructures. So if you watch the two one after the other, you might understand more of what's going on. We've got some really good tools for analysis. If we've got SEM and we use the backscattered mode, we can see the average atomic number, and that helps us sort out which phases are richer in the higher average atomic number, because they look lighter than the ones which are lower. And then SEM, in using the secondary electron mode, we can check for holes by tilting and looking for the edge effects. You don't want to analyze holes because the signal could get disrupted, and then you lose part of the signal and you might get inaccurate results, and you don't want that. And then EDX on the SEM, you get to the actual phase compositions, although with light elements there can be problems, and carbon is a real pig because there's so many problems with carbon and contamination. Then we use X-ray diffraction to analyze the phases and the structures, so we can actually confirm what we've got from before. And some people like to use thermal analyses to give you the reaction temperatures. I'm not going to deal too much, apart from this bit, I'm not going to deal with that at all actually, because that's something in its own right. So comparing scanning electron microscopy with light microscopy, we've got secondary electron mode, which is topographical, and we can see fracture surfaces, pores and holes. And then we've got backscattered electrons, which show the average atomic number, so the phases. And then we've got energy dispersive X-ray spectroscopy, which give us the compositions. These days, people don't use light microscopy as well as they used to, because we tend to be a bit lazy and go to SEM. But you can do absolutely amazing things with light microscopy and with different etching. And the interference methods and polarized light can also tell you something about the structures, whether those particular phases are isotropic or anisotropic. So light microscopy is still a very powerful tool. So when we're analyzing microstructures, we want to check the sample for homogeneity. This is a really good idea, because is the sample what we think it is? I'll show you an example in a minute, because if it's not homogeneous, then you're going to have different areas with different compositions. And it's also good to look at the sample in low magnification, just to check if it isn't full of holes or whatever. And at the same time, you're looking for homogeneity. You use backscattered electrons to identify the phases, which will have different contrasts due to the average atomic number. Now, you can have phases with similar average atomic number, so you need to check the morphologies and consider the formation sequences. Think of the interpreting microstructures presentation that I've done. You need to check holes, if we've got any holes, with secondary electrons, and you do that by tilting if you cannot see the edge effects. You do not analyze holes, because the results are likely to be inaccurate and a waste of your time. So here we are at low magnification. The micron bar is 1 millimeter. That sounds a bit of a misnomer, but we always call it the micron bar. So this is really low magnification, and we can see that we've got bits of the components that never melted, and we've got some nice holes there as well. I'll talk about that in a minute. So we know our sample is not homogeneous. Okay, so if you had time, what you do is remelt this and hopefully get the sample you want. And then looking at the low magnification first, we've seen that shows you the general idea of the sample. Just imagine what would happen if you'd gone in, whacked up the magnification to the highest, which is what students tend to do. You go in there, you really wouldn't understand what's going on. But if you looked at it in low magnification first, you would see this unmelted bit although there has been some solid state transformation in it by diffusion, surrounded by layers of something, and here they are at higher magnification, and then you've got this two-phase matrix with a whole load of holes in, and you can see that you've got what we call an edge effect. On one side you've got that bright, almost light thing, that's an edge effect, and it's one thing telling you that it's a hole. Okay, that hasn't got any edge effects, so it's probably not a hole. Okay, so if you can't see this on your dark areas, then you would have to tilt the sample and see if they are holes, and you do not analyze holes. Now, sometimes if you've got complex specimens, I think this had at least 4 components, if not 5, you've got very similar contrasts in backscattered electrons, which are telling you that these round bits and the matrix they're in have got similar average atomic number. That's a pain, and you have to be very, very careful. This was a horrible sample, but you'll see a bit more of it later. And then considerations for analysing. Strictly speaking, and there is a standard on this, EDX is the technique and the results. EDS is the actual spectrometer, so EDX. And then it's also important to take overall analyses at low magnification to check the sample composition and homogeneity. Try and avoid holes. Okay, if you've got 2 phases, then if you plot them out on ternary paper, obviously this is for samples with 3 components, and you plot them out. If you've got 2 phases, the overall should lie on the line joining the 2 phases, or if you've got 3 phases, the overall should lie inside the triangle. Otherwise, you've got, if that doesn't happen in a ternary, you've got phase missing, or you've got an inaccurate result, at least one of them, and you suspect the smallest thing that you're analysing. Okay, it's a good idea to do 5 measurements on different areas of the same phases. Then you can work out an average and present it with a standard deviation, and then you can see how good your results are. So here's a ternary done by one of my students, and if you look here, you've got 3 phases, and the overall, so little circles are the phase analyses, squares are the overalls. So here you've got the overall inside 3 phases, that's lovely. Down here you've got 2 phases and the overall is off to one side. Okay, so there must be another inferred phase down there. Here you've got 2 phases and the overall is just on one side, so that's sort of okay. And then here you've got a bit of a mess, but we know there's another phase over there. So this is a nice check. Here you've got 3 phases and the overall is actually on the edge. If you've only got a minor amount of this phase, then that's okay. So it's a very good check to do. And this just shows some of those samples that we were referring to in the previous one. You've got dendrites and eutectics between. Here you've got an oxide, and if you've got yttrium in the sample, yttrium always wants to form an oxide, and we tend to ignore that because we were trying to work out what was going on with yttrium, ruthenium, nickel. Although the first phase, the primary phase, quite often solidified on that. Not a nice system at all. Right. This is very important to try and explain why you try and analyse the largest areas you can find. If you imagine there's the beam and you're looking sideways through your specimen, that's what you see. That little bit is what you see on your surface and on the screen when you do a spot analysis. And sometimes people think, oh, if I put that spot on that area, I can analyse it. No, it doesn't work like that, because what happens is the incoming electrons interact with a volume. Secondary electrons comes off first at the top, that's why it's topographical. Backscattered electrons come from a deeper area, and X-rays come from an even deeper area, and roughly it's 2 microns across and 2 microns deep. So if you're only analysing a small patch, then you're going to be picking up the matrix as well. Okay, now the size of that interaction voltage does depend on interaction volume, does depend on the accelerating voltage. It's larger for higher accelerating voltage, but you can't just say, okay, we'll turn down the acceleration voltage, because it must be sufficient to excite the X-rays of the samples that are in there. So higher atomic number elements need higher accelerating voltage. Okay, and the other thing, the system might have been calibrated for a certain acceleration voltage, and higher atomic numbers have larger interaction volumes. Okay, so bear that in mind. But if you always try and analyze things that are bigger than 2 microns across, then hopefully it won't matter that you're picking up signal from 2 microns down. It's very, very important. So let's look at what's going on. There's that little schematic thing again. These are in different scales. Your dot looks like my laser pointer. It's an electronic laser pointer. And you might think, oh, I'm fine because it's sitting within there. But remember the interaction volume, and there's 2 microns. So if you think you're analyzing that small precipitate, again, this is a section, you're actually picking up more of the matrix than the small precipitate. So what you want to do is go and analyze large precipitates, so that this thing, and put it in the middle, so that this thing is sitting well within. Okay, so here are some real results, and the student was measuring these things bright. Okay, so he measured the bright there, and he got what he thought was good results. Now, that's 5 microns, so that's about 2 microns. It might not be exact. If you imagine putting that on there, your 2 microns actually covers hardly any of that bright area or that bright area. So neither of those analyses are going to be any good for the bright area. Same poor old student, and he analysed a hole. Okay, and this is what happens in the hole. I haven't drawn the electron beam going down, but I've just got X-rays coming off at random directions, because you wouldn't have one electron, you'd have a beam of electrons. That's why I've got these bouncing off. So don't analyze holes, you're not going to get accurate results. And then this is another example from someone else. Just a reminder, it spreads out beneath the surface to round about 2 microns, and so there's 2 microns. There's my little circle I've drawn on as a guide. This is fine. That's going to pick up this. This is maybe fine. That's going to pick up the dark. That is on the edge. I don't know why he put it on the edge. And he's mainly going to be analysing the matrix. Okay? And it's amazing. Something's gone wrong. It's amazing how people can do things wrong. If you want to analyze an area to get the overall composition, you look for nice areas like this. Now this is a bit low mag, but it's not too bad. That's 300 microns. And what I'm doing is I'm avoiding visible defects like cracks, because that's the same as a hole and holes. This bit is horrible because you've got holes and cracks and don't know what else, and that could reflect the signal, reflect the X-rays, and you get an inaccurate answer. So here's place, and you would look for the largest you could find. Okay, can take a while, you've just got to put up with it. Here's another analysis, 10 microns, so that's about 2. So that one's horrible, don't know why he's got it on the edge again. That one's less horrible, but he's going to be picking up some, as is that one. That one's totally horrible. Number 3 is okay because you can't see any other phases. Okay, so most of those, that, and that, are horrible. This one's okay, that one's iffy, but it's not as bad as the others. And then here, same thing. It would have been better to, instead of analysing there, to go in there, because this is bigger than that neck, or even to go in there. So pick the biggest areas to analyse. You can measure single phase regions with spots or boxes, but definitely use a box to measure where you've got two phase regions. And be careful what's going on here. There's some areas which have been analysed, but he could have picked this area of dark to analyse, and be careful of what's in there, because that's not single phase. It looks like two phases. And then here's some more stuff that was being analysed. Now, he hasn't chosen the biggest. Look at that, it's small. He could have chosen that for the dark, and he could have chosen this or that for the light. And then this does more of the same, but why not measure this, analyze this nice big area for medium? Sometimes you have to spend ages finding bits that are nice enough to analyze. By nice enough, I need big enough. Now, when you do your EDX analyses, what you need to do, you do need to look at the peaks, but it's better when you report them, unless you want to show something on the peaks, it's best to report numerically. So what we've got in here, you can see a lighter region, there's some more in there, and what that was is contamination with gold, because they've been making gold samples just before they made these samples. So those are some pitfalls for X-ray diffraction, for SEM, EDX. Now I want to talk about X-ray diffraction. Powder is better to avoid preferred orientation. More about that later. But normally it's easier for us to use bulk or solid because we've already got that. We need flat surfaces. And the samples must all have the same condition, so use metallographically prepared samples, okay, the mirror finish and all that. And very important, for your phases, use the same reference for the same work or project, so you're not referring to different references for the same phase, because there's going to be various versions in the database, and when you check which one you want to use, make sure it doesn't say replaced by and give you another number. Very important to do that. And then you check what phases should be there. You know the elements, hopefully. If you don't, you do SEM EDX first, and you would know the composition temperature range, especially for a complex system. So try and find out as much as you can. I usually do SEM first before XRD. I know a lot of people who are older than me would do XRD first because that's an older technique and they're more comfortable with that. But I prefer doing SEM. Then I've already got an idea of what the samples look like and what the compositions are, and I know how many phases I've got. So then I do XRD to find out what they are, the structures of them. And this just shows what happens if you have a rough surface, so it wasn't prepared metallographically. And you can see, first of all, we've got low counts, okay, 60, that's pathetic, okay. The maximum should be at least 2,000, rough thumbsuck. We've got a huge background. I mean, look at this background compared to the highest peak. It's nearly a third of the highest peak. That's rubbish. And also, underneath that background, you've got some peaks hiding. And you might say, oh, you can see them there, but only because you know they're there. Okay? So get nicely prepared samples and don't waste your time. And then you can have an effect of texture in as-cast samples, so the peak intensities are different from the standard. And you can get shifts in the position, the peak positions, to theta values because of solid solution. A lot of people when you try and publish your work, want Rietveld analysis for greater accuracy, but the results will be compromised if the patterns aren't good. So if you've got a crummy pattern, using Rietveld isn't going to help really. You'll just think you've got better stuff than you have, and it's still rubbish. If you're doing something totally new, you might get a new phase that is not in the database because you've just discovered it, or you're the only one to realize it's a new phase. So those peaks might not be there, but some of those peaks could already be shared because you've got the same atoms in there. Right, let's talk about preferred orientation. This is a classic picture of an ASCAR structure. And you've got the chill grains, the columnar grains, and the equiax grains, and it really depends the proportions of these as to the difference between the melting point and the pouring temperature. But this just shows all of them nicely. And what happens if you look at these regions, they are orientated the same way. So you've got preferred orientation. And what's going on when you first pour that in the mold, you get lots of nucleation, and those are the chilled grains, and they're pointing out all over the place, okay? And then some of them, a little bit later, some of these just happen to be facing the right way. So this one and that one, and then they can grow and push out the others. So this one's been pushed out, that one's been pushed out. They've been cut off. So that's standard pouring into a mold. We do a lot of our samples, we make them with arc melter because it's a very good way to make samples. Not all samples, but most samples. And what we get is something like that. So look what most of the sample is. We've got that preferred orientation. And what we invariably do with our samples is we cut it down the middle. So we've got a story of what's going on. So we're going to have preferred orientation. Some people anneal them straight away, but we like to look at them first and then we anneal them. Then there's a thing called Vagard's law. And this is niobium molybdenum. There's the phase diagram. I've chopped out the molybdenum. And you can see it's a really boring phase diagram. It's just an isomorphous solid solution going across. And as you add molybdenum into it, the lattice parameter is coming down because molybdenum is smaller than niobium. And this is Vagard's law, that it's the lattice parameter is directly proportional to the size of the substituting atoms. There can be deviations, and it's just going to be not quite linear, but overall it will still go the same way. So that's Vagard's law, which is very useful, okay? And then one of the things you can do, I stole this from a book, is there's some samples and you could use this to try and work out what the phase diagram was. So here you've got a single phase region and Vagard's law is, and it's doing something on Vagard's law. So from this we know that B atoms are bigger than A atoms because the lattice parameter is going up. Then here we've got a boundary and we go from a single phase region to a two phase region, and because the compositions of the phases in that region are this for one phase and that for the other, there's not going to be a change in the lattice parameter because you're always looking at that phase of that composition and that phase and that composition, so it stays the same. Here it's what we call a line compound. Very difficult to actually do that, get a line compound. It usually slides off. That should be more curved. It usually slides off and you get a little bit of the other phase. Again, we've got constant lattice parameters because you're looking at one phase of that composition and one phase of that composition. Then we've got a couple of samples in here. Pure B is 8 and another solid solution there, and it's forming solid solution and it's obeying Vagard's law, okay? So those things are good to remember. And then here's a nice example. We've actually changed this, but this phase diagram is nice and clear. See, that's dotted. We've changed our minds about what's going on there. So in here, the alpha titanium phase, it's got a very short extension. So you're going to get little variation in the lattice parameter. This phase beta has got a big variation, so you're going to get a larger variation in lattice parameter. Okay, when you have it at lower temperatures, unless you stabilize it with something else, it will transform to these two, but never mind. But I'm just taking this as an example. Now, what can happen is if the difference, because you've got a wide solid solution, if the difference is large, it might be too far for the software to recognize. So you've got to look for patterns and compare. And then this is what we call a line compound. It's got virtually no variation, and so that should have no variation in lattice parameter or peak positions. And then what we had in this sample, totally different sample, was there were two phases and they both had the same structure. Okay, well, how do we know that? Because we've got pairs of peaks. Okay, there's a pair, there's a pair, there's a pair. The other one is just sitting there and we just can't quite see it. So be aware of things like that. Now, what happens? This one, it's just to try and show you something quickly. If you've got a cubic crystal, then you've got fewer peaks and they're quite large. Then you go to tetragonal and some of those split up. So we've now got two peaks in some positions. So you've got more peaks, but they're going to be of lower intensity. Then we go from tetragonal to orthorhombic. Now they're all split up into three, apart from this and that one. And so you've got even more peaks and they're going to be of lower intensity. Okay, so the message of this is the simpler structure you've got, you'll go, and cubic is pretty simple. You can't get more simple than cubic, is you're going to have fewer peaks and they're going to be stronger. The more complex you get and the more you get away from cubic is you're going to have more peaks, here they are splitting up, and they're going to have a lower intensity. Okay, so less symmetrical structures have more peaks and the intensity decreases. And then the other thing that can happen is sometimes the major peaks can be very, very similar. So if we look at this, we've got some phases of aluminium copper, and we've got peak at 2.05, peak near 2.05, peak at 2.05, in that phase, and that phase. Okay, so you might run into trouble trying to work out which is which. That's where, having analysed it, you would know where it is. So these are all the peaks for delta, these are all the peaks for gamma, and these are all the peaks for eta, and they've all got a high peak at 2.05. Okay, nasty, there to trip you up. Whoops. This isn't letting me go back. Sorry about that. The other just showed an example where you had two phases with very similar atomic numbers, and they had very many peaks in that sample because there was a lot of phases in there which were complex. Right, now this is a dubious bit of identification because first of all you've got one peak only for this and for that phase, silicon, and that's bad because you should have, apart from carbon, which has only got a small number of peaks, and depending on what range you use, you might only find one. I know, I've checked that. All the others should have more than one peak. So you can see this one has got 3 peaks. Okay, so that's very dubious. And then on the other hand, you've got some peaks here which aren't identified. So this was very bad identification. Thank you very much. And remember, this is a companion presentation to interpreting microstructures. Thank you.